fins can be fully evacuated and thus will be the largest vacuum chamber ever constructed. The elimination of air resistance is vital to the concept. To reach space, the projectile is to reach a velocity of 12,875 kilometers per hour. That is a really hard throw. If not in a vacuum, at such a target velocity, the air in the chamber would cause enough friction to destroy the entire system. At the end of the spinning arm, constructed from carbon fiber composite materials for extra strength and light weight, is a mounting point for the orbital projectile. This rocket-shaped capsule is also made from carbon fiber, while the tip is made from super-hardened metal alloys capable of withstanding the incredible forces that come to play during a launch. We are talking around 60,000 Gs of centrifugal force right before the launch. Once the projectile with an estimated payload capacity of up to 200 kilograms has reached the predetermined velocity, it is released at just the right moment to leave the chamber through the exit tunnel, passing hyperspeed doors and finally breaking through a sealing membrane and shooting toward the sky. That sounds simple. The entire centrifuge will be built at a 35-degree angle to send the projectile on an orbital course. After reaching an altitude of about 60 kilometers, the capsule needs to activate its integrated cheat mechanism for the final push into orbit. It is a small rocket engine, without which even Spin Launch's lunatic spinning speed would not accelerate the projectile enough to reach full escape velocity. So far so good. Super fast spinning arm released just at the right moment and boom! We're headed to space. But would this actually work? The answer would be a careful yes. The science behind this project is solid. So solid that Spin Launch secured considerable investment and is already experimenting with smaller sized centrifuges. Orbital experimentation is targeted to start in 2026. Is it worth the research though? I think that's also a yes. If they build it and it ends up performing as they had planned, the per kilo cost of payload to orbit could be as low as 30% of the cost of a conventional rocket. As for its limitations, one problem is scalability. The bigger you build these centrifuges, the more exponentially the forces involved will grow. With today's materials, you cannot go much larger than the planned 100-meter diameter to assure safe operations. You know, boom! Another one is linked to immense forces. It is the amount of G-forces the projectile and the payload need to be able to endure. As mentioned, we are talking major forces here in the region of 60,000 Gs generated during the half-hour spin-up period. Half an hour. So the system is not an option for just any payload that needs to be delivered to orbit. How high is the crazy factor of Spin Launch? I rated a comforting 4 out of 10. This thing has the potential to become a reality in the not too distant future. Let's move up a tier and have a look at a concept known as StarTram. This is something known and beloved by sci-fi fans. StarTram is a mass driver. These machines offer a rocket and propellant-free method for launching payloads into space. While mass drivers have been a concept in speculative fiction since the late 19th century and various engineering designs have been proposed, significant technical challenges have hindered their development so far. But today we are a lot closer to mastering the required technology for such a mega project. Let's explore what this concept is all about and what it needs to be constructed, if ever. The first component is magnetic levitation, or maglev for short. This technology is already in use in public transportation today. It is the key to ultra-high-speed trains that can routinely run faster than 500 kilometers per hour. An improved version of maglev technology has been developed for Japan's next generation of Shinkansen trains. This SC maglev, or superconducting maglev, can deliver improved performance by utilizing superconducting magnets in its propulsion system. The entire train rests on a magnetic field. It doesn't touch anything, it floats. This L0 series prototype train holds the record for the fastest crewed rail vehicle, with a record speed of 603 kilometers per hour. And the speed can be improved further if you eliminate the main factor of resistance, air. Just like with Spin Launch, air resistance is the main enemy. In the case of the space tram, this can be achieved by running the vehicles in a vacuum tube. This way, speeds of multiple thousands of kilometers per hour can be achieved. Very fast. While the method of propulsion is not that outlandish and very much possible to build with today's technology, the next element needed for StarTram is a whole different story. While the physics behind the concept is solid, its scale is a bit daunting. That is because we would need to build a constantly rising tube that extends over 100 kilometers in length. And that tube needs to rest on something, right? It can't just float in mid-air. Enter magnetically suspended superconducting cables. Sounds complicated, but it's actually straightforward. When opposing electric currents flow through two conductors, they experience a repulsive force that pushes them away from each other. Electromagnetism. This force increases with the current flowing through the conductors. And again, an emerging technology can help extend this principle's capabilities, and just like the launch vehicle's magnets, superconductivity is the key. These cables are conceptual for now, but they are already under development for superconducting power grids, and they can carry currents that go up hundreds of megaamps. Dr. James Powell and Dr. George Mays, the inventors of StarTram, say that a suspension system that has one superconducting cable on the ground and one suspended in mid-air above it can provide a levitating force of 4 tons per meter of StarTram guideway. And they could even generate this force if the two conductors are separated by a jaw-dropping 20 kilometers. So, having found a method to suspend the maglev track in its vacuum tube kilometers above the ground takes us straight to the next technological challenge. The floating track needs to be secured to stay in place. Under normal circumstances, the first thought would be to just tie it down using steel cables. Now, this is fine for the first few kilometers of track, but the higher it floats above the ground, the longer the cables get, and at the same time their weight increases too. This, unfortunately, is the cause of two problems. One is that at some point the weight of the cables will inevitably be larger than the levitating force the superconducting cables can provide. The other one is an even bigger problem for the next space launch concept I will explain in today's episode. Tethers have a breaking length. The breaking length is the length a tether made from a certain material can reach before it will break under its own weight. The weight of a cable gets so large at some point that it rips itself apart. But there is good news for StarTram enthusiasts. Modern synthetic fibers can already deliver the capabilities to span the tens of kilometers needed for this launch system. The final technological ingredient needed to cook up a StarTram is called MHD. Or magnetohydrodynamic pumps. Say what? In principle, this is not a new technology. It has been used for pumps, generators, and thrusters for many years. In its use case for StarTram, MHD will become the invisible barrier at the far end of the launch tube. I mean, somehow you need to seal it up while something passes through. This MHD window will allow ionized gases to be continually expelled from the tube. It's like a see-through vacuum pump. With this neat little trick, it is possible to keep a near vacuum and still have a tube with an open end for the vehicles to shoot out of. This, in short, is the concept for a more or less realistic mass driver. For a less crazy version of this, you could of course just accelerate a rocket with it. In this example, we have Rocket Lab's Electron endure a bit of a push, build a much shorter tube at 1 kilometer depth into the ground and use it to accelerate the rocket up to about 300 meters per second of velocity. That's fast. This animation is from Tim Dodd, the everyday astronaut, who we're collaborating with on this video. To learn more about the challenges and math behind such a project, check out his video as well. It's very much worth it. Tim, you rock. I always wanted to say that. Now it is time to ask our questions again. Is this a realistic technology? The surprising answer is yes, it is less far out than a first glance would make you believe. Is it worth the effort? If the system runs anywhere nearly as efficiently as its inventors think, we are looking at the capability of launching thousands of tons of payload per year into orbit for less than $40 per kilogram. That's nothing. Two proposed versions have been presented. One is a cargo-only version featuring a 100-kilometer-long underground tunnel with a bend upwards for the last kilometers that could be mounted to the side of a mountain. While this is much cheaper and easier to build than the levitating version, it could not be used to launch humans due to the immense G-forces coming into effect while changing direction upwards at the end. For crewed launches, StarTram would need the levitated tube version with a steady incline. What are the limitations of this technology? Let's keep aside the immense cost of constructing such a gigantic project. In that case, the main limitation lies in the maximum payload capacity of the individual launch vehicles, much like the fairings of rockets today, and their maximum lift capabilities. But such a system would compensate for these limitations with an unprecedented launch cadence. With enough electrical power, this system could launch multiple times per hour. And how high is the crazy factor for Startrap? This concept looks way more far-fetched than it is. I would not put it higher than a 5 of 10 on the crazy scale. Building it based on today's leading-edge technology is possible, with a budget high enough and a government or mega corporation willing to see this through. And from here on out, things are getting really crazy. If I told you that it was seriously considered to nuke a spacecraft to orbit, you might think that I am joking. This idea from the 1940s was explored to a great extent. The United States Air Force, DARPA, and NASA all conducted studies in the 1950s and 60s to find out if this next concept was viable. It was DARPA's predecessor, ARPA, that really got this idea going when they decided to fund and sponsor a program with the name Project Orion in July 1958. The leading scientists for Project Orion were Ted Taylor and Freeman Dyson. And yes, this is the Freeman Dyson who also theorized the Dyson sphere. Both were accomplished and very intelligent physicists, and especially in the early stages of development, high hopes were attached to this project. Werner von Braun, who was convinced that Project Orion was the best option for a human exploration project to Mars, actively supported this. NASA's mission profile for this proposed a 125-day round-trip mission with a crew of 8. That is ridiculously fast. Even now, it feels like a utopian goal, as today's technology would not allow for the kind of speeds required to achieve such a short round-trip time. Alright, spill the beans. What is Project Orion all about? How does it work, and why could it have offered unmatched speeds over 65 years ago? The idea behind it is to use a form of propulsion that harnesses nuclear power. But we're not looking at nuclear batteries like they have been used on probes and satellites for decades. Project Orion wanted to use nuclear fission bombs to propel a spacecraft. Nukes, you know, the things that go boom. Seems simple enough. Detonate a nuclear bomb under the spacecraft and ride the shockwave upwards. Once the craft reaches the point at which it would start to fall back down, it releases and detonates another nuke from the bottom of the craft. Bloop. You'd repeat this until the craft reaches the desired speed. From today's point of view, we are inclined to discard this idea right away. No one in the right mind would seriously consider detonating dozens or even hundreds of nuclear bombs for a single spacecraft launch. But the physics behind Project Orion are sound. Preliminary testing was performed using conventional explosives. Using this method, the scientists were able to reach about 100 meters in altitude in a model test. The clever engineers even found a surprisingly elegant solution for the problem of the insanely abrupt acceleration inevitably tied to an explosion. The bottom of the Orion spacecraft, called the pusher plate, would be connected to the upper station via 2 sets of shock absorbers. They would then act as a buffer, temporarily storing some of the energy exerted onto the plate. The result would be a linear acceleration converted from the impulses of the detonating bombs. 2 ship sizes were envisioned for testing: interplanetary missions and advanced interplanetary missions. Each was planned to use as many as 800 bombs to reach a LEO of about 480 kilometers. The needed yield of each bomb ranged from 0.3 kilotons for the test article to 0.35 kilotons for the advanced interplanetary spacecraft. They would then act as a largest version temporarily of the nuclear Orion spacecraft would be exerted onto the plate, boasting a diameter of 56 linear acceleration conversion.
Enemy force sighted on the horizon.
Autopilot mode disabled.
Enemy destroyer detected. Enemy aircraft carrier sighted. Enemy battleship sighted. Enemy destroyer sighted. Enemy battleship detected. Enemy cruiser.
Our team has taken the lead.
Spotter returning to ship. Autopilot mode enabled. Autopilot mode disabled.
Enemy destroyer detected. Enemy battleship sighted.
Water airborne.
Enemy cruiser sighted.
Spotter returning to ship.
Enemy cruiser sighted. Enemy battleship sighted.
Anti-aircraft gun crews are on full alert. Torpedoes to starboard.
Enemy destroyer sighted.
Torpedoes astern. Anti-aircraft gun crews are on normal alert. sir. Torpedoes astern. Torpedoes to starboard.
The enemy team has taken the lead.
The ship is on fire.
Enemy destroyer sunk.
to win. The enemy team has taken the lead. Battle ends in 5 minutes.
Autopilot mode enabled.
General quarters.
Awaiting instructions.
Enemy force sighted on the horizon.
Autopilot mode disabled.
battleship detected.
Spotter returning to ship. Attention, reporting the target position.
Enemy cruiser detected. Enemy battleship detected.
The enemy team has taken the lead.
is on fire!
The enemy team has taken the lead.
Problem solved, sir. Spotter airborne.
Enemy cruiser detected.
Spotter returning to ship.
Enemy battleship detected.
Target penetrated.
The enemy is about to win.
Torpedoes, dead ahead.
The enemy is about to win. The enemy team has taken the lead. begins in 5 minutes. The enemy team has taken the lead.
Autopilot mode enabled.
Battle starts.
Awaiting instructions.
Enemy force sighted on the horizon. Enemy cruiser sighted.
Autopilot mode disabled.
Enemy cruiser detected. Enemy battleship sighted. Enemy cruiser sighted.
Concentrate fire on the designated target.
Enemy battleship sighted.
Reporting the target position.
Enemy cruiser sighted.
Target penetrated.
We've sunk an enemy destroyer.
Enemy battleship detected. Enemy cruiser sighted. Enemy battleship detected.
Stations. Reporting the position of a strategic target. Signal on fire. Problem solved, sir.
Enemy cruiser detected.
Enemy cruiser foundered.
Enemy battleship detected.
Attention. Reporting the target position. fire! Good game, everyone. Protect the base. Problem solved, sir.
Target penetrated.
Spotter airborne.
Enemy cruiser sighted.
The ship is on fire! Problem solved, sir. The ship is on fire. Spotter returning to ship.